Okay, so good morning, everybody. Welcome to our class. Mm, Okay, so today I'm going to finish talking about. Good morning, Aman. Density of states, and then after that I will start talking about we call it what do you call it? Angular momentum. Okay. So in the density of states problem, I forgot to mention in the previous class that for the simple cases of for what do you call it, two-dimensional potential well and 3D potential well, we actually can calculate the density of states for large values of the energy, and there's a fairly simple way to do that. Okay. So the idea is that you consider again, so we have for a two-dimensional potential well. Okay, sorry, I forgot to start the screen sharing. Right. So again, for a two-dimensional potential well, what we have is that we can write down the energies as expression pi square and pi square h bar square over, what was it in the last? Right, so there's some factor off somewhere. Again, I'll leave that to you to discuss, to work that out. Okay, there's a factor of 2 that I'm not getting right. So this is the expression for the density, for the energy for a particle in a two-dimensional potential well. Okay. Now, so what do these states correspond to? These states correspond to so each of these points in this plane, where this is M and this is N, right? Each of these integer points corresponds to a single value of the energy. Now, if we consider a large value of the energy, so let us consider a circle or a segment of a circle in the plane like this, whose radius is r, let's say. Okay. Then you can see that what this energy is, it can be written in terms of the radius of the circle, right? It can be written as pi square square it. So I'll just call all of this some constant alpha or alpha naught times r square, right? So r, all right. So for instance, if you look at this point, whatever m or n is, so now this circle, you can see it intersects some of these points, but not all of the points, right? So every point on the circle is not a physical energy state, right? But that's okay because we want to get an approximate idea of what's going on. So what we do is we make another circle like this, let's say, and now what you can see is that between these two circles, right, in the region that lies between these two circles, this region, right, there is a certain number of states which you can see which lie within this region. So I can mark those in red, let's say, like this. You can include these points which are on the boundary also. Okay. We can get an estimate for how many states lie in that region. So let's say the width of this region is delta r, right? So what is the area of this region? Area will be given by 2 pi r delta r, right, divided by 4. Why 4? Because we are taking 1/4 of the circle, right? So it becomes pi r by 2 delta r. Okay. So this is the area in shaded in red. Now I can ask how many states lie within that little segment. Okay. Now you can see that the states are all equally spaced, right? So if I look at any set of neighboring states like this, right? There is a certain area which is sandwiched in that unit cell. That area, so area per unit cell is just 1, right? In units of mn, right? So this is like a dimensionless area, okay? So how many such unit cells within that segment? So the number of unit cells is equal to the total area of the region divided by this A naught, right? But this A naught is just 1. So the number of unit cells is again just pi r by 2 delta r, okay? And this is an approximation because like I said, this is all the states which lie on the circle, all the points which lie on the circle do not correspond to physical states, right? But and also this n has to be an integer. Now, if you look at arbitrary values of this radius and arbitrary values of this delta r, then n will not necessarily be an integer, right? But that's okay, because we are going to look at the limit of large energies, and the limit of large energies, n will become a large number, and we won't be so worried about what happens between the integers. Okay. And now we can compare this to the expression for the energy. So I can write this as E naught times R squared. So this R is dimensionless, right? It's m plus n are just numbers. And so the rest of this has dimensions of energy. So E is equal to E naught times R squared. So I can express this n in terms of E, right? So what is R? R is equal to E by E naught square root. And what is delta R? Delta R will be 1 by 2 root E naught times root E times delta E, right? Just using the derivative dr by dE, right? Okay, so then this n of E so I should call this d of n, because this is a differential number of states. This is a differential, right? This is not the total number of states, it's a differential number of states. So dn is equal to pi by 2, r is root E by E naught, delta R is delta E by 2 root E naught times A. Okay. So we see this factor of E cancels out, and we are left with pi by 4 root E naught, not root E naught, sorry, pi by 4 E naught times, we can write this as dE. So finally we have the result that dn E by dE is equal to pi by 4. And this comes out to be a constant, right? So in the previous class, I had given you some examples of density of states of various substances. And I told you, for instance, that, in some cases, for instance, in this case, in 2 dimensions, the density of states is a constant. So that is what the result we get. N of E, so this is, so I should write this as dn by dE. That is what we mean by density of states. N of E is the total number of states, is a constant. And one thing you can see is that, let's say that you were to do the same calculation for a 3-dimensional potential well. What would happen is that here you would get one more number, right? But now instead of an area, you would have a volume, right? For 3D potential well, the energy would be equal to some A naught again plus 3 integers. And again, we would repeat the same procedure, but now instead of an area, we would get a volume, right? And the volume of the shell would be 4 pi r squared delta r, right? So the difference is that in for the 2D case, you are getting R delta R. For the 3D case, you're getting an extra factor of R, right? You're getting R squared delta R. So once again, if you ask what is this dN? dN will be the total volume divided by V naught, which would again be just 4 pi R squared delta R. And then if you want to write this in terms of, so this is equal to E naught times R squared. So once again, we have that R is equal to root of E by E naught. So dr is equal to 1 by 2 root of E naught times E times dE. And so dN becomes 4 pi R squared. R squared is E by E naught. And dr becomes dE by 2 root epsilon naught E. Right, now you see that there is a factor of E in the numerator and a factor of root E in the denominator. So the E does not cancel out. So this dN becomes 2 pi root E over E naught times root E naught times dE. So which tells us that the density of states for a three-dimensional system goes as is proportional to root E. So to compare to the what I explained, what I gave you in the other day, this corresponds to something. If you make a plot of this dN by dE, it's like this. Okay, so the number of states as a function of energy is increasing. All right, and again, so this is something that is very important whenever you do any kind of statistical mechanics or thermal or statistical properties of substances. Okay. Okay. By the way, let's see. Okay. All right. All right. So now we can start our discussion of angular momentum. Okay. Are there any questions about this? So in a general statistical mechanical problem, what will happen is that you will need two things, not just the density of states, but also the occupation probability. So the occupation the probability density function. The probability density function tells you, depends on, for instance, whether your system is bosonic or fermionic, right? So if you have a bosonic system, you will use the Bose-Einstein distribution. For fermionic systems, you will use the Fermi-Dirac distribution. And then you would multiply that probability distribution function with the density of states to get the final probability of occupation of any energy level. And that probability will ultimately be used to calculate any statistical averages. Okay. All right. So now let's talk about angular momentum. So what is angular momentum, and why do we have a whole separate section related to angular momentum? Well, in classical mechanics, you have the definition of angular momentum, as r cross p, right? So if I have a particle which is moving, so there's some x, y, z, and you have some particle that is moving on some trajectory. And then I ask, what is the angular momentum of this particle with respect to the origin, let's say, or with respect to an observer at the origin. Then angular momentum is given by this expression, right? So now one can ask, well, what is the operator equivalent of this angular momentum? The operator equivalent would be, well, r hat cross p hat. And if we work in the position representation, what happens? The r just becomes the vector r, right? Position just becomes the position eigenvalue, which is just r. And the momentum becomes this operator, the gradient operator, right? So the angular momentum operator becomes this expression, r cross r times the gradient. So if I write down the components of this, let's say so this is a vector, right? Because r is a vector, gradient is a vector, cross product gives you vectors, right? So let's say I ask, what is Lx? So Lx is IH bar, and then you will get y times dz minus z times dy, right? Why is this? The vector, what is the vector r? The vector r is just components x, y, z. What is the vector corresponding to the gradient? Dx, dy, dz. So I'm just taking the cross product of these two vectors, right? Okay, is this fine? Any issues? Please ask me if you are not familiar with something, okay? Similarly, I will have Ly, same way, IH bar, Z dx minus x dz, Lz is equal to minus IH bar, x dy minus y dx, okay? So now there is one very important difference between the classical and quantum angular momentum. For the classical angular momentum, if you take Lx, right? So Lx will become ypz minus zpy, and Ly is equal to zpx minus xp. Okay. Now the thing is that if I can ask, for instance, what is the Poisson bracket between have you talked about the Poisson bracket in classical mechanics yet?
No, sir, not yet.
Not yet. So the Poisson bracket, right, is the classical version of the commutator. So if you have any two functions, f and g, which are defined on some classical phase space, then your Poisson bracket is written as, so these are functions of your phase space coordinates. Then this is the definition of your Poisson bracket, where qi and pi are your generalized coordinates and generalized momentum. right? And f and g are some arbitrary functions on phase space. Okay. Now, so for instance, if I ask what is the Poisson bracket of xi with pj, right? What do I get? I get 1. And if I ask what is the Poisson bracket of xi with xj, that's equal to the Poisson bracket of pi with pj. That's this. Sorry, not 1. I get delta ij. Now, so I can ask what is the Poisson bracket of Lx with Ly. Okay, and we are talking about a single particle with 1 degree of freedom. Well, we are in 3 dimensions, so there are 3 degrees of freedom, x, y, z. So how would I write down this Poisson bracket? It would be d Lx by d xi, I is equal to 1 to 3, d Ly by d pi minus d Lx by d pi, d Ly by d xi. Okay. So now I can work this out. Let me work it out. Copy and paste. So what is dlx by dx? 0, because Lx doesn't depend on x. Dlx by dy is equal to pz, dlx by dz is equal to minus py. This part minus py. Similarly, dlx by dpx is 0, dlx by dpy is equal to minus z, dlx by dpz is equal to 1. So on and so forth, right? So I can substitute this into my Poisson bracket. See what I get. X and y. So dlx by dx, dly by dpx, dlx by dpx, dly by dx. So this is for the x component, and I will have a similar one for the y component and the z component. So I'll just call this x. So what is it going to be? Well, this one is just, this term is just 0 because I know that Lx doesn't depend on x. And then this term is 0 because I know that Lx doesn't. So there's a 0. Then I can ask what is the y component. Dlx by dy, p1 dlx by dy. Okay. Now once again, I know that here I have dly by dy, right? So Ly will not depend on y, and Ly will not depend on py. So I'll get 0. Then I can ask what is the z part, right? Dlx by dz, dly by dpz, dpz, dly by dz. Okay. So now what is dlx by dz? Dlx by dz is equal to minus py right? And similarly, what is ly? Dlx by dpz, this is going to be equal to x. Why? Because if you look at the definition of ly is equal to zpx minus xpz, right? Just by the cross product. So dly by dpz will be minus x. Sorry. Minus. And the same thing, dlx by dpz. What is dlx by dpz? Is y. And minus y. And then dly by dz will be px. Okay. So what is this? This is equal to xpy minus ypx. Right? But now we recognize this to be equal to Lz. Okay. So similarly, so what do we have? We have Lx, Ly, the Poisson bracket of Ly and Z is Lz. And in general, we can write down that if I have Lij, the Poisson bracket will be epsilon ijk Lk. I mentioned what this epsilon function is before, right? Do you all know what this is, or should I explain this again?
Yes, sir.
Yes, what? Yes, you know.
Yes, we know.
Explain it. You know. Okay, good. It's just a useful way of writing down components for the cross product, right? So this is the Poisson bracket. Now, what about so this is for the classical functions. But now the thing is that it doesn't matter what the Poisson bracket really, what it is, because it ultimately does not affect measurements, right? In classical physics. In classical physics, you can have two quantities which have non-zero Poisson brackets, but you can still measure those quantities simultaneously. Okay. But in quantum mechanics, what happens is that if you have two operators whose commutator is not zero, right? Then A and B cannot be measured simultaneously, right? Right? And why is this? Because if you remember, what does measurement do? Measurement collapses your system into an eigenstate of the operator which you are measuring, right? Now, if A and B don't have eigenstate,
Hello, sir.
okay?
Hello.
But then because
Sir,
yes,
your voice is
who was
gone.
that? Sorry, anything?
Sir, your voice was gone for a while.
Is it coming now?
Yes, sir. Yes, sir. Yes, sir.
Okay, so I'll start. So A and B cannot be measured simultaneously because A and B don't commute, so they don't have the same set of eigenstates. In other words, they cannot be diagonalized simultaneously. So if I measure A, the system collapses into an eigenstate of A. So if you measure A, the system collapses into an eigenstate of A. Let's call that psi A. But psi A is not an eigenstate of B. Right? So that means the expectation value of this operator B is not well determined. B is not well determined on psi of A, right? Because psi of A is some linear superposition of eigenstates of B. And similarly, if you measure B first, what will happen? Your system collapses into some eigenstate of B, but then this is not an eigenstate of A. So by the same reasoning, A will have some uncertainty when you are in this eigenstate B. So that means A and B, they cannot be measured simultaneously, right? There will be uncertainty, and that uncertainty is represented by the fact that you can write this expression right, the general uncertainty principle for any two operators. And if A and B don't commute, then this is zero. This is not zero, right? So what happens with the quantum mechanical operators? Now let's look at the quantum mechanical operators. We get Lx. So we just get this usual factor of IH bar. Then we have ypz. Oh, sorry, not ypz. Yd dou z, because this we already have this minus zpy. And then we have, let's say, Ly is equal to minus IH bar Z dou x minus x. Okay, then I can ask what is the commutator of these two operators.
Sir, Z del Y, you have written PY.
Thank you. Okay, so what is the commutator? The commutator is, I'll get minus h bar squared. And then we have the commutator of all these various terms. Rho dz minus dy, comma. Do you all have a class at 9 o'clock?
No, sir.
Okay. All right. Well, I'll finish after calculating this anyway. Okay. Now we can look at the various terms in this expression. So let us look at y dou z commutator with z dx. Okay. And again, how do I calculate such commutators? Anybody remember?
Sir, by placing a function psi on the right hand side.
No, that is fine. I mean, I can place a function, but I don't need that function, right? I can. So, no, it's okay. It's okay. Say hello. Come say hello. Come say hello. Okay. Say hello. Say hello, people. ठीक है? दरवाजा डाल दो, तुम्हारा बहुत लाउड है। Well, you are forgetting that when I do this, when I have products like this, right? What do? I can use this identity. Remember that?
Yes,
Okay.
sir.
And then I can do the same thing for the second term. So then I will get y times, for the second term, I will get z dz dx plus y times dz comma z dx, so on. Okay. So when you do this calculation, what you will find is that, so I'll leave the calculation as an exercise. So you will find that Li Lj is going to be equal to IH bar, then IH bar, yeah, I think there'll be an IH bar, epsilon IJK LK. Right. So the angular momentum operators, they don't commute with each other. And this lies at the heart of the theory of angular momentum. Right? So because these operators don't commute, this means that we cannot measure Lx, Ly, and Lz simultaneously. Okay? Or in other words, they don't have simultaneous eigenstates. There is no vector, there is no state in the Hilbert space, which is an eigenstate of both, of all three, or of any two of these. Okay. All right. So what does that mean? That means if we write down a quantum state, it can be an eigenstate of only one of these operators. Right. So conventionally we call that, we use Lz as that operator. Right. So we look at eigenstates of Lz. But so these operators don't commute, but there is another operator that does commute with all three of these operators. So you can write down L square. Now what is L square? That is the total angular momentum squared. Lx square plus L square plus Z square. Okay, am I audible?
Yes, sir.
Okay. So this operator L square is commutes with all of the individual components Lx, Ly, and Lz. This is an exercise. You should show this. Okay, so that means if I make a choice of L square and any one of the three components, okay, so I can take L square and Lx, or L square and Ly, and L square and Lz, right? Those two will commute with each other, right? So I can pick L square and Lz, right? Then these two commute with each other, right? Or I can pick Lx and Ly, doesn't matter. since they commute with each other, they will have simultaneous eigenstates. So that means that that is state of in terms of angular momentum, eigenstates. So let's say that an eigenstate of L square has an eigenvalue. We normally use the letter J to denote the eigenvalue. So we have a state with total angular momentum. So this will turn out to be equal to something called some J times J plus 1. Okay. We will see why later on. And then the eigenvalue of Z on this same state. Okay, so this is the same state, is M. So we can write down this state as, we can label it using these eigenvalues. Okay, so a given state of the system can be labeled using an eigenvalue of L square and Lz. And what we will see later on, for instance, is that M, the allowed values of M, they go from minus J to minus J plus 1 to J minus 1 comma J. And we will, and that J is equal to 0, 1 half, 1, 3 halves, 2, so on. Right? And this becomes very important when we look at the most important system, which is the hydrogen atom, right? Why is the hydrogen atom so important? Because, well, solving the Schrodinger equation for the Coulomb potential, that tells us that electron orbits are quantized, right? And it tells us that we have this picture of how atoms absorb and emit energy in discrete, frequency intervals. So now, well, everything is not hydrogen. So a lot of things are, you have helium, you have lithium. And if you try to solve the Schrodinger equation for more than 2 particles, you can't solve it exactly, right? But even if you can't solve it exactly, you can still continue to use the same picture of atomic orbitals. And there is something called the linear combination of atomic orbitals. You can assume that states of an electron in, for example, a system like uranium or rubidium or any complicated atom. The states of the outermost electrons can be written as some linear combination of the basic elementary orbitals, and those orbitals are classified according to the angular momentum, right? So you have and then they're classified within that angular momentum by the Z component. Okay. So the picture you have of this angular momentum is the following: that you think of something which has, so you have a particle, let's say, and it is spinning around like this, right? So you imagine a spinning top, okay, and that spinning top, right, has a total angular momentum L pointing in this direction. but then that top is also precessing around this vertical axis, and around this vertical axis it has some angular momentum Lz. So this becomes the orbital angular momentum, and this becomes the azimuthal or angular moment, or the magnetic. This is also known as the magnetic quantum number, right? Because in a magnetic field, for instance, what happens is that this Lz, right? So what is this Lz? This is the spin degree of freedom of a particle, right? So for the simplest case of J is equal to 1/2, what are the allowed values of M? -12 and +12. And what is that? That is, those are simply the states of a spin 1/2 particle. So we'll talk about all of that. We'll talk about spin 1/2, and then it becomes very important to understand how to add angular momenta. And that is also we will cover. So a good preparation for this would be to revise your polymetric algebra, okay, which you covered in the beginning of the semester. All right, so I will leave it here. Any questions?
So the picture we have shown here, Lx and Lz.
You're not. Your voice is not clear, Yash.
Am I audible, sir?
Yeah, better.
Yes, sir. Sir, the picture we have shown on the last page, it is for the single particle, right? So how can we make this picture, draw this picture for many particle systems? Can we do that?
So for more than one particle, it becomes difficult to draw such pictures. Okay, but we will see what we can do in our later lectures. All right. Okay. Any other questions? Okay.
Sir, one more, sir.
Yeah.
The commutation property we have written like L square and Lx with commutes. How can we set up an experiment in keeping in mind that? Like, can we do?
Yeah. So. Yeah.
Measure L square. How can we do that?
Yeah. So we can measure. How do you measure L square? That's a good question. Let's think about this. So I'll think about it and get back to you. Okay. No, but that's a good question. All of the theory doesn't mean anything unless you can actually perform measurements, right? Okay. All right, then I'll see you all tomorrow morning.